here today, logged in and listening to this talk. I'm going to give an overview of additive manufacturing and lightweighting with polymers. And of course, along the way, we will introduce some of the activities that we do here at Case Western Reserve University. So I'll be happy to entertain your questions after the lecture. What is innovation? And this is a good point to start for our discussion today. Innovation essentially allows us to take what is an invention and transition it to something of value to the point that somebody is willing to pay for it or use resources to gather it and convert it to useful products. So innovation is beyond invention. In fact, when we talk about bridging between science and society, applied engineering or applied science enable us to take what is good, a good basic platform coming from a university research program to something that the market demands or customers are willing to pay for. And in between, this involves collaboration with industries and companies. Okay, so let me start by showing you to you some of the important aspects of materials. Bulk materials are monoliths, are essentially solid-state systems that are produced through a manufacturing process. Another way of looking at it is the bulk material may define the thermomechanical properties, but eventually it's the surface that interacts with the environment. So one aspect that we pay particular attention in our research and may have important implications in additive manufacturing is coatings or preparation of the surface. And you will find this whether you're dealing with packaging materials, iPhone, skin, automotive coatings, high-performance coatings, etc. So what I'm trying to emphasize here is the bulk monolith property is one thing, but also is the interface. So let's begin this question, what is additive manufacturing and 3D printing? To do that, I would like to juxtapose discussions on polymers as well. Polymers are high molecular weight molecules or materials that are typically polymerized by two types, addition or step polymerization methods, which can produce different types of architectures like linear polymers, cross-linked polymers, branch systems, and dendritic systems. On the other hand, what we actually see around us is plastic, packaging, paint, textile, fiber, or even waste. So plastics is a more popular term for polymers or macromolecules. So that means they have to be processed, they have to be manufactured, formulated, blended, and so on. In fact, at the molecular level, they can be quite as complex as your DNA, protein, or can assemble itself, viruses, supramolecular assemblies, or even knotted systems. In fact, when we talk about polymers, we might as well talk about nanomaterials. Depending on the dimension, molecular weight, solubility, they can form complexes, gels, micelles. So in one aspect, it is treated as a colloidal material, or it can form films, very, very thin films or membranes with very high order, such that they can be classified also at the nanometer range or ultra-thin films. As such, polymers are also true nanomaterials. However, polymers, as we know it, we use the term plastic, but more appropriately, thermoplastics is a good term because it means that a polymer can be deformed by temperature, heating it up, okay? On the other hand, there are certain types of polymers that do not easily soften, do not easily change its shape. There's a general term called thermosets that we use to define them. And they are high performance in the sense that they have engineering properties that can replace metals, or sometimes the industry called non-metallics. Either way, we're dealing with high performance materials, commodity polymers like polyethylene, polypropylene, etc. These are things that we see or encounter every day, and hence polymer is ubiquitous to materials all around us. Now, if we look at the price versus tensile strength, this gives us an idea that most of the high-performance polymers are typically more expensive, but then they have excellent thermomechanical properties that enable us to use them as practical replacement for metals. In fact, you can look at traditional materials in society like wood, fiber, leather, steel, different types of alloys, ceramics. All of this, in principle, can be replaced by plastics or polymers. And hence, it's a matter of processing them and looking at the price-performance ratio. That is why in the automotive industry, there's a lot of interest these days, including the aerospace industries, on carbon polymer composites. Carbon polymer composites enable one to replace steel or aluminum in terms of their thermomechanical properties as well as stress. Polymer fibers or carbon fibers can be produced from precursor polymers, which involves that of curing, cyclization, or aromatization. Many types of lightweighting properties that you hear these days from automotive companies actually involves that of looking at carbon polymer composites. So for example, if you look at this car, this Toyota Camry, we can see that even though it has a metallic body, many parts can be replaced by lightweight composites or even directly with polymers such as your tires, your paint, your engine covers, inverter cover, timing belt, engine cover, inverter cover, and especially in the interior, many things can be classified there as based on polymers. The drive towards using nanocomposites is to basically increase the mileage by which these cars are rated in terms of federal specifications. Now, let's review as well what are the traditional methods for processing plastics. Plastics can be produced by extrusion. That means you need to heat it up, melt it, and then you extrude it through a twin or single screw extruder. The melt comes from pellets or solids that are heated up and through a hopper, and then once it's extruded out, it can be quenched by cooling either in air or water. And so what you see are finished products that came from an extruder, and this is a very common way of processing rods, molded parts, etc. Injection molding then is a variation of extruder. In that case, you use a mold to create a shape where the compounded plastic or thermoplastic is mixed, of course, with different additives that gives it color, aroma, gives it plasticization properties, biocide, etc. And therefore, a plastic is actually a compounded material or a mixture. Other than injection molding, polymers can be made also by thermoforming, which means you apply a heat and a mold which can be accessed through changes in vacuum, pressure, or even mechanical stamping. So going over this, one may ask, where is 3D printing? Is 3D printing a part of what we normally see as processed plastic? 3D printing, although plastic is just one of the materials used, is actually very important in the polymer or plastics world. In other words, many types of plastics that are normally processed through high throughput methods like extrusion or molding can be 3D printed. And 3D printing means that you have a three-dimensional object that can be created through a printer, quote unquote. The printer actually is a programmable robot that has the ability to melt and extrude a filament, for example, as one form of printing. So in this case, we might as well define what additive manufacturing is. Additive manufacturing is when you add materials to produce a three-dimensional object. starting from a digital file that can be used to control the movement of a mechanical arm or a robot, basically, that allows you to add the material at specific locations or thicknesses. So the technology means that you add a material. This is against the definition of subtractive manufacturing. Subtractive manufacturing is when you remove material to create an object. A good example would be sculpturing or machining or lithography. So those are subtractive manufacturing versus additive manufacturing when you actually add a material. So there are several types of additive manufacturing technology. One of the most common and perhaps the least expensive is based on fused deposition modeling, or FDM. What it is you melt the plastic, extrude it, and then add it. Another is based on lithography or stereolithography, where you actually polymerize, sinter, or form the object through very specific movements of precise mirrors and motors. Sintering is a big process that involves melting of metals or plastics. There are several of them called selective laser sintering, SLS, direct metal laser sintering like DMLS, and so on. So all of these are really alternatives towards direct subtractive manufacturing, metalworking, or machining, which can be in the type of casting, fabrication, or stamping modes, even though plenty of automation methods exist for subtractive manufacturing. 3D manufacturing tends to be slow. Here again is a list of all the different methods of 3D printing. So as a summary, you direct the material where you want it to deposit or polymerize or sinter. That means from an original computer-aided design, this directs the machine or the robot to move on an X, Y, Z scale. Some of the more common polymers that are 3D printed includes ABS, polycarbonate, HDPE, polyphenol sulfone, etc. In fact, polymers can be blended, added with filler materials or composites, or you can make with copolymers or use even metals. So let's highlight some of the differences of 3D printing, additive manufacturing versus high throughput manufacturing. The possible advantages of additive manufacturing is that you have low volume production, you can work with increased complexity and design, increase part functionality, or improve even some of the environmental sustainability, either of the part or the manufacturing process itself, because you require only a few pieces. And that means that you have to develop new supply chains or retail models. The best advantage can be summarized by this following statement. On-demand, limited production, high-performance parts, complicated geometries, this will lead to value-added products that magnifies the advantage of 3D printing. Another way is to look at this graph that shows increasing geometric complexity on the x-axis and cost. That means that these are higher margin, higher profit systems with limited production. Or you can look at a complexity versus number of materials. That means that traditional high throughput methods tend to have less complex design but higher lot sizes. On the other hand, additive manufacturing tends to give you smaller lot sizes but higher complexity. A manufacturing gap actually exists. That is, it's desirable if 3D printing can be made as fast as high throughput manufacturing. But this seems to be a major challenge on the instrument suppliers. So as I summarize, 3D printing materials are mostly thermoplastics. These are plastics. These are thermoplastic elastomers that essentially change its shape with heat. Okay, metals can be 3D printed. Okay, so you may be familiar with these polymers like nylon, polycarbonate, ABS. Okay, but high-performance thermoplastics, even ULTEM has its role because these essentially are engineering polymers that can replace metals. So another way to survey the type of materials that can be 3D printed is shown in this list. And you can even see there that it's possible to 3D print metals. And usually this is done by sintering methods. Now, there are other methods of 3D printing, not only FDM. Selective laser sintering means that you start with a resin or powdered metal in which the laser is used to heat up or sinter these particulates at exact positions. And the object is built up such that at the end of the SLS process, one can remove the object from the original unsintered material because they have been melted together. Another way to look at 3D printing is based on an inkjet principle, where the material is actually delivered as an ink or a liquid formulation, and then it adds material on top of each other to build up the object. This does not necessarily mean that you have to melt it, but you deliver it as a solution or a viscosified melt. Photopolymerization and 3D printing, what's the relationship? Well, polymers can be made by using monomers and initiators and cross-linkers. Photopolymerization means that the polymerization itself can be initiated by light, precisely UV light, and therefore you need to deliver that light precisely where the monomers are present and initiate polymerization. This is done by using DLP methods, or digital light processing methods, which are micromirrors or lenses that direct light at very specific spots. This is not too different from the technology you have with LCD projectors, in that high precision of or movement of lenses allow that photo curing or photo initiation to take place with the monomer. And this allows us to actually make 3D objects all the way to the micron level. So the best way to produce objects that are at this level is not by FDM, but actually a form of SLA. And the polymerization means you can direct that polymerization all the way to microlithography type of resolution. Again, as I said, the weakness of additive manufacturing, 3D manufacturing, is that it is slow. On the other hand, there are companies that are trying to modify or improve the speed by which the parts can be produced. In other words, it becomes more economical if one can produce a higher throughput of a more complex part. On the other hand, this has to be overcome in terms of how these polymers are polymerized or melt processed. I do not have it on this slide, but there's actually a company called Carbon 3D that have found a way to accelerate up to about 100 to 1,000 times the process of 3D printing using traditional thermoplastics. Now, one advantage of 3D printing is that you can actually scan an object and convert it into a digital file. So this is exemplified by a simple scanner that one can use to digitize any object and then convert it to a file, which can then be 3D printed. Okay. So making parts is one of the most important directions by which 3D printing can get into. As I said, 3D printing traditionally has been around, has been used by the military and bigger industries to produce prototypes. The challenge is how to make a object that actually replaces a manufactured part. And there are several weaknesses, there are several failure mechanisms. I may or may not have time to discuss that today, but essentially anything that competes with a high throughput production process like extrusion or molding will have differences not only in terms of speed, but by also how the materials are deposited, which can produce failures due to delamination, for example, or poor bonding of layers. Nevertheless, let's say with metal materials, ceramics, polymer materials, they can actually be manufactured even with higher complexity. So you can see all these different types of materials that have been reported, and the list of the polymer materials in particular, PEEK or PEEK is of high interest because these are traditionally molded parts with high performance specifications that can operate under high pressure or high temperature conditions. Again, these are some of the possible industrial applications ranging from automotive to aerospace to medical, electronics, consumer. In fact, the medical aspect is quite interesting because this is used for orthopedic implants, dental, etc., which can be formed from a digitized file of body parts or parts that can be imaged using, let's say, MRI or CAT scan methods. So in other words, the high value added function here is that you can make very precise implants that can replace their natural equivalent. Now, in combination with 3D printing, you can actually use different types of traditional manufacturing processes, whether you're dealing with powders or nanocomposites that can be printed and then cured or pre-cured, or combine it with subtractive manufacturing, then you can form the desired part you want. Or in other words, complexity is not a problem and can be addressed not only with 3D printing but by combining it with other methods. Again, more pictures of possible applications of 3D printing. So these are parts that have been used or manufactured, okay, as well as in electronics. So for automotive application, a good demonstration was shown that one can demand on-site a car by 3D printing. And here, for example, is a Strati model. This was a car that was 3D printed on-site. I don't know how long it took to 3D print the whole car. So important questions arise in terms of what is the role of 3D printing in manufacturing. Is it scalable? Can one have a higher throughput? What parts can only be made by 3D printing alone? Okay, so those are important questions. Another is this Shelby Cobra that was 3D printed, and obviously this is a retro car. This is a car that's popular, and here one can rate a classic car or a car that is not manufactured anymore, and by 3D printing one can reproduce a classic car or create a variation of a classic car with new parts. So you can see that in the automotive industry there's a lot of interest not only on lightweighting but being able to print or form on-demand parts. Here is a picture of 3D printed car. The message here is that you can have a car that is very economical, lightweight, and does its job, or does it not? So 3D printing is of high interest again to the automotive industry in terms of making on-demand cars or even just parts. Okay, so parts for the automotive industry may include replacement engine parts or things that can be used as high performance seals. Okay, in other words, there will be a lot of demand on the printed material itself in order for it to replace what has been a traditionally formed, molded, or extruded part, both with metals and non-metals. So the bigger question is, when will 3D printing transform into a real part manufacturing uh, uh, proposition where the performance of the printed part is equal or greater than that of the original part. So for now, many are looking at 3D printing for making bigger objects, rapid objects, but a vast majority of them is considered still a hobbyist type of proposition, or a lot of the inexpensive machines there is basically a hobby enterprise. Just to give you a picture of the 3D printing market and application, this shows you the areas where 3D printing is expected to gain market share or revenue. The graph here shows the type of materials that are printed. Very, very clear. Lots of the 3D printing technology is dependent on polymers or plastics. Here are some of the manufacturers and the market share they have with the printing machines. Here are some of the reasons why people pursue 3D printing, whether it's to improve the design, to prototype, to increase this improve the supply chain model, reduce the cost, but essentially there has to be a transition from prototyping to product development to the actual manufactured product itself. So we're not far from finishing our talk. We can summarize the things we discussed in terms of perspectives. One, additive manufacturing is a growing ecosystem that utilizes new and prototyping manufacturing models. The advantage is that it allows creativity for creation of more complex designs, and therefore is ripe for commercialization and new materials development. Perhaps in combination with subtractive manufacturing and high throughput manufacturing, it complements that of all other manufacturing methods and perhaps rival these traditional manufacturing methods in the future. Cost of 3D printing has definitely gone down, and the functionality has also increased. What is clear here is that polymer materials are going to be very important in terms of how we move forward from prototyping to actual product manufacturing. And this means that the industry or academia has to introduce new types of materials that are blended, synthesized, or even recycled for the industry to use in order to make those prototypes viable as actual parts. Key properties in both processability and finished product should be a focus. Promising direction, perhaps in the use of nanocomposite materials to improve thermomechanical properties, more carbon-based composites, photocurable systems that can add more functionality, the use of bio-based feedstocks that are renewable, or even recyclability. So the message here is that it's open for scientists, engineers, materials, and of course hobbyists to improve the process and the possibilities for 3D printing. So it is ripe for innovation, technopreneurship, and one of the best places to observe this perhaps is in the automotive industry. So with that, I'd like to thank you, and I'll be happy to answer any questions you may have.
All right. Thank you very much, Professor. So, as he just noted, we are now entering the question and answer portion of today's presentation. I do see a couple of questions that were submitted via the questions module and the chat module, so please send them in. In the meantime, I'll go ahead and pose a couple of questions that we had received during the lecture for the professor. The first one we received was, what is your view of HP's multi-jet technology, and how could that impact the aerospace and automotive industries?
It's a very good question. As you know, HP is well known for printers, inkjet printing, laser printing. That technology is quite an improvement in terms of throughput, ability to use complex designs. But one of the key drivers that needs to be overcome is really not only the speed, but the viability and stability or thermomechanical properties of the produced part. So this is a big question that even the HP process may not be addressing properly. One of the failure mechanisms that I wanted to address was that in layering plastics or thermoplastics, the polymers are essentially quenched to form solid-state materials. And solid-state materials do not necessarily have good adhesion between surfaces. So each time you deposit a layer, for example, with FDM, and once you quench it, you expose it to moisture, air, water. These are areas which are sources of failure or delamination between added layers. And polymers is not so much as the structure and chemical composition, but also the way they are processed allows one to control what they call crystallinity and amorphous state of the polymer. So by adding them as individual layers in a layer-by-layer fashion, those crystallinity and amorphous properties are confined and not ideally addressed as a single monolith object, as opposed to materials that are extruded, crystallized, or spun as fibers. So that is one of the basic things that needed to be overcome in the whole 3D printing technology.
Very good. We have a second question. What kind of innovative materials are you seeing in the market?
Okay, so I'm of course favorable of extending the performance of these 3D printed materials even towards extreme conditions. That is, can these materials last a higher temperature? Can it withstand abrasion? Can it withstand pressure? What are some of the polymers that can do that as a replacement, let's say, of metals? And so I am very interested in high-performance materials like PEEK, ULTEM, PPS, even Kevlar that can be 3D printed to actually manufacture parts other than using molding methods or extrusion methods. So if one can do that, then truly one can produce high-performance parts, limited amount, high complexity, and high performance. Another type of material that I'm, of course, interested are composites or nanocomposites. So, for example, one can introduce graphene, nanotubes, different types of nanoclay particles that can improve not only the thermomechanical properties, but the barrier, diffusion, or stability of these materials. One can have features that are not easily accessible with other traditional methods. And then lastly, there's also a lot of interest on recycled or renewable or bio-based materials where you can recycle a part after it has been used and it will have another life as a 3D printed object, or you can use bio-based raw material sources versus petrochemical-based polymers.
All right. Our next question. What are the possibilities of 3DP for research?
For research. So yes, definitely. Research means that you use it to create something new or discover. 3D printing, by virtue of taking a digital design into an actual object, can be used to test different complexities or structures that otherwise would have been harder to produce with different materials. So, for example, different model architectures that test compressive strength, flexural strength, even different types of foam, cell structures, and so on. Another is by rapid testing or high throughput testing of materials. So for example, if you can 3D print different objects useful for mechanical testing, and you can rapidly 3D print different compositions or different compositions on a complex part, one can look at the combination of structure, composition, complexity, or different processing conditions, and how they may play an important role on the actual application. So in other words, 3D printing is a research tool as well. It's not just a manufacturing tool, but it can be a research tool to test designs and materials in a laboratory.
Okay, our next question. How difficult is it to mix two layers, for example, graphene materials with thermoplastics like PLA?
So there are two ways. You can, of course, mix them or blend them as a master batch, mix them, compound them to form a filament, or there are 3D printers that allows you to print two or more different thermoplastics. So that means with an FDM, you need to start with an A material and a B material, and then co-print them together. The B material could be a composite that already contains your graphene or nanotube, and therefore when you print them, it goes to where you want it to go, either through different 3D structures or even as alternating layers. There are machines that can do that.
Excellent. Our next question, most manufacturing devices utilize multiple materials in their construction. Are there 3D systems available that can use multiple materials at the same time during construction, like polymers and metals?
Yeah, the question there really is if the material is processable in the same manner such that you can print them simultaneously with a single type of machine. So for example, with sintering, definitely one can combine resins with polymers and metals if you want to are able to match them properly in terms of their sintering properties. On the other hand, you can have a melt processable material such as plastic and then combine them with a sintering method. Now, I'm not sure how easy is it to combine or cross over two different types of printing methods. So the match there is that as long as you're using one type of machine, both materials should be within the boundaries or parameters of operating that machine. So if it's FDM, then both materials should be melt processable, whether it's metal or polymer. If it's sintering, then both materials should be processable by laser heating, either as a metal or a non-metal.
Very good. Our next question. What is the typical material utilization percentage for 3D printing polymers and metals?
A good question. Basically, with molded parts, and if I understood the question correct, I'll try to answer it two ways. 3D printing is a precise printing method with, I would say, highly efficient use of the original or raw material source versus other types of subtractive manufacturing which actually waste material if it's not part of the mold or it has to be removed or chipped off or machined. So that waste material actually is recycled on some manufacturing processes or simply thrown away because they cannot be recycled or processed. On the other hand, I will answer this question in terms of what materials percentages are used. Majority of the 3D printed materials are plastics or polymer based.
Okay. Now we have another question. How far away are we from 3D printing a simple semiconductor device like a computer chip or a solar cell?
Good question and quite complicated. So if you break down that problem, there are probably a majority of the parts, monoliths, substrates, different types of connectors, perhaps that can be integrated and 3D manufactured. On the other hand, very, very small parts. If you think about lithography, definitely this is not the realm of 3D printing yet. But one thing is possible. One can make micron, 100-micron objects by 3D printing using stereolithographic methods. And so complexity is only as good as, of course, the machine and the material you use. And traditionally, SLA is based on another lithography methods is based on a photopolymerization or resist material. So majority of the more complex and smaller parts out there are polymer-based. Metals, a majority of them are simply processed by sintering. On the other hand, one can make metals by basically using metal precursors, metallization, coating with metals, and even ceramics. Ceramics can be made with pre-ceramic precursors. So for example, polymers can be aromatized together with several additives and converted into carbides or different types of carbon-based materials.
All right. And just a couple more questions in the queue now. The next one reads, how does the government address the additive manufacturing technology in terms of safety for the commercialization of products?
I'm not sure of any particular regulatory body that's looking at it, and I may be wrong. It could be lack of awareness on parts. I know that NIST, which is the standards arm of the Department of Commerce, is interested in understanding the requirements, performance, and testing of 3D printed parts. One can, of course, go to ASTM, ISO, or different bodies like underwriter laboratories to see how they evaluate different parts, printed parts, in terms of their thermomechanical properties, flammability, toxicity, and so on. So a good starting point really is the material itself. What has been done or what has been used to characterize the standards based on the material. On the part itself, of course, the more complex objects, different types of compositions, I believe new standards can be set eventually that not only looks at the composition but actual usage of those materials and how they are degraded, abraded, or recycled.
Understood. And now, the last question that we have in the queue so far, are material properties, are they as equivalent to conventional injection molding, or are they something superior in 3D printing? If so, why?
So the answer there is they're not. Most cases, they're not. The reason is that because of the additive manufacturing, as I explained, you are basically taking multiple steps in quenching, let's say, an extruded material versus a monolith. And by doing so, you expose each quench material to the atmosphere. Sometimes this has been improved by different methods of saturating or controlling the environment. I don't have the slide here, but some companies like Carbon 3D have patented a process by which 3D printing can be made without these defects directly by polymerizing or forming the monolith from a precursor polymer. That is, you don't go through the quenching step. And I believe many materials and methods will eventually come that can overcome this problem. But so far, the weakness of 3D printing is that they do not have properties equivalent of extruded, molded, or higher throughput form materials such as we have now. The basic property that one can look at is in terms of any processing condition that allows poor control of crystallinity versus amorphous content, specifically for polymers, or the inability to control the crystalline domains monocrystalline grain boundaries of metals will result in poor properties. So all of these fundamental properties can be addressed by, let's say, investigating these properties using microscopy or spectroscopy. But in general, 3D printed parts have this poor control all the way to the molecular level.
Okay, and with that, you can always reach either myself, Gerald, at Park Systems, or Professor Advincula at Case Western Reserve University by email. And the professor's email address is here on the title slide of his presentation, rca41@case.edu. If you have any questions at all regarding Park Systems or the atomic force microscopy solutions that we offer for nanoscale research, you can reach us at www.parkafm.com. Or if you have any questions about this presentation or any of future presentations, you can also reach me at gerald@parkafm.com. Really quickly, I'd just like to point out that this is an ongoing lecture series that we are doing with Professor Advincula. And we've also dived into previous topics that are from different industries, different applications as well. And those are all also publicly available at parkafm.com through the Learning Center. As for our next topic, it will be October 15th. We'll be talking about smart nanocoatings. Is that right, Professor?
Yes, I'm excited to deliver that lecture. If you can, October, our next topic will be smart and nanostructured coatings. And if you're in the Cleveland area, you're welcome to participate live here at Case Western Reserve University.
Excellent. And details for that particular lecture will be going out via email shortly and will also be up at parkafm.com. Any parting comments for the audience today, Professor?
Yes, thank you very much for attending our lecture. And also, again, thank you for Park AFM for hosting this series. Until next time, goodbye.